The era of light, the cooling of the universe, the prelude to change. As the universe expanded, it also cooled. After the chaotic and explosive conditions of the first few minutes, when temperatures soared high enough to facilitate nuclear fusion, things began to stabilize. By the time the universe was about 380,000 years old, the temperature had dropped to approximately 3,000 Kelvin. This cooling marked the beginning of one of the most transformative periods in the cosmos, the formation of the first atoms. For hundreds of thousands of years, the universe had been a seething plasma of charged particles, protons, neutrons, and electrons, moving so rapidly that they could not combine into stable structures. These particles collided constantly, interacting with photons, particles of light, in a chaotic dance that kept the cosmos opaque. Photons, unable to travel far without scattering off electrons, were trapped, effectively imprisoned in the primordial fog. This state persisted until the universe cooled enough for something extraordinary to happen, the birth of neutral atoms. The era of recombination, the first neutral atoms. Around 380,000 years after the Big Bang, the universe reached a critical milestone. As the temperature dropped below 3,000 Kelvin, the kinetic energy of the electrons decreased. Freed from their frenetic motion, electrons began to combine with protons and other atomic nuclei to form neutral atoms. This process is known as recombination. The term recombination is somewhat misleading, as this was the first time electrons combined with nuclei to form atoms. It was a monumental transformation that altered the very nature of the universe. Hydrogen, the simplest and most abundant element, dominated the process, with helium and trace amounts of lithium also forming neutral atoms. The birth of neutral hydrogen atoms was especially significant. Hydrogen's simplicity, consisting of one proton and one electron, made it the first atom to stabilize. Helium nuclei, which had formed earlier during the Big Bang nucleosynthesis, required two electrons to become neutral, but the lower abundance of helium meant hydrogen dominated the cosmic landscape. The decoupling of matter and light. One of the most profound consequences of recombination was the decoupling of matter and radiation. Before this period, photons constantly collided with free electrons in the plasma, making the universe opaque. However, as electrons bonded with nuclei to form neutral atoms, photons were no longer scattered as frequently. For the first time, light could travel freely across the cosmos, unhindered by interactions with matter. This decoupling marked the end of the universe's opaque state and the beginning of its transparency. The photons released during this era are the same photons we detect today as the cosmic microwave background, CMB radiation, a faint glow that permeates the universe and serves as a relic of its early history. The cosmic microwave background, a snapshot of the young universe. The CMB is often referred to as the baby picture of the universe. These photons, now stretched into microwave wavelengths due to the universe's expansion, provide a wealth of information about the conditions of the cosmos at the time of recombination. Discovered in 1964 by Arno Penzias and Robert Wilson, the CMB is one of the most important pieces of evidence supporting the Big Bang theory. It is nearly uniform across the sky, with slight fluctuations in temperature. These tiny variations, on the order of 1 part in 100,000, correspond to density differences in the early universe. These variations would later grow into the large-scale structures we see today: galaxies, clusters of galaxies, and vast cosmic voids. Why recombination took so long? Given that protons and electrons are naturally attracted to each other by electromagnetic forces, one might wonder why it took nearly 400,000 years for neutral atoms to form. The reason lies in the high energy of the universe's photons during its early stages. Before recombination, photons carried enough energy to ionize any newly formed atom. Whenever an electron and a proton combined to form hydrogen, a photon would immediately knock the electron free, keeping the plasma state intact. Only as the universe cooled did the average photon energy drop below the ionization energy of hydrogen, allowing stable atoms to form. This delay ensured that recombination occurred simultaneously across the entire universe, creating a remarkably uniform environment. This uniformity is reflected in the near-perfect isotropy of the cosmic microwave background, CMB. The role of helium and lithium. While hydrogen was the star of recombination, helium and lithium played supporting roles. Helium atoms formed when two protons and two neutrons bonded together, requiring two electrons to become neutral. Helium nuclei had been created during Big Bang nucleosynthesis, but were much less abundant than hydrogen. As a result, helium accounted for about 25% of the universe's baryonic matter, compared to hydrogen's 75%. Lithium, though present in trace amounts, also participated in recombination. However, the conditions of the early universe were not conducive to the formation of heavier elements. Stars would later become the factories for elements beyond lithium, producing carbon, oxygen, and the rest of the periodic table through nuclear fusion and supernova explosions. The beginning of the cosmic dark ages. The formation of neutral atoms and the decoupling of light marked the beginning of a new era, the cosmic dark ages. With no stars or galaxies yet formed, the universe was a vast expanse of neutral hydrogen and helium. Although photons now traveled freely, the absence of luminous objects meant the cosmos was plunged into darkness. During this time, the gravitational pull of denser regions of matter began to draw material together. These regions, formed from the tiny density fluctuations observed in the cosmic microwave background, CMB, would eventually collapse under their own gravity to form the first stars and galaxies. However, this process took hundreds of millions of years, leaving the universe in darkness for a significant period. The significance of recombination in cosmic evolution. Recombination was not merely a chemical process, it was a turning point in the evolution of the universe. By allowing photons to decouple from matter, it set the stage for the development of large-scale structures. The release of photons during this era also created the CMB, a treasure trove of information about the early cosmos. Moreover, the transition from a plasma to a neutral state profoundly altered the universe's behavior. In the plasma state, the movement of charged particles was dominated by electromagnetic forces, creating a highly interactive environment. Once neutral atoms formed, gravity became the dominant force, guiding the growth of cosmic structures. How we study recombination today. Modern science allows us to study recombination with remarkable precision. The CMB is the primary tool for understanding this era, and advanced telescopes like the Planck satellite have mapped it in exquisite detail. These observations reveal not only the conditions at the time of recombination, but also clues about the nature of dark matter, dark energy, and the universe's ultimate fate. Theoretical models of recombination rely on both quantum mechanics and general relativity. By simulating the behavior of particles and photons in the early universe, scientists have developed a comprehensive understanding of how and when neutral atoms formed. Connections to modern cosmology. Recombination also provides insights into some of the universe's greatest mysteries. For example, the uniformity of the cosmic microwave background, CMB, raises questions about how distant regions of the universe, which could not have communicated with each other due to the finite speed of light, share the same temperature. This puzzle, known as the horizon problem, is addressed by the theory of cosmic inflation, which proposes that the universe underwent a rapid expansion before recombination. Additionally, the study of recombination has implications for the search for dark matter. Certain models of dark matter predict subtle variations in the CMB that could reveal the nature of this elusive substance. A legacy of light. The era of recombination and the formation of atoms marked the end of the universe's chaotic infancy and the beginning of its structured evolution. The light released during this time still travels through space, carrying with it the story of the cosmos's earliest moments. As we study this era, we gain not only a deeper understanding of the universe's origins, but also a sense of our place within it. The atoms that make up our bodies were forged in processes that began during recombination, linking us to the very birth of matter and light.